We often will need to measure hydraulic head very accurately. If we want to determine a hydraulic head gradient, for example, then we need to take the difference between two hydraulic head measurements. And in order to take the difference between two measurements, each one has to be made fairly accurately. And so in order to make these accurate measurements, what we have to do first is have accurate measurements of the top of the wellhead. So the technique that we'll use to do that will be surveying. Basically, in order to do surveying, what you'll use is an instrument that is set up like a telescope. Various components on the instrument allow you to determine the angle that this telescope is pointing. Here's kind of a classic transit, this old brass transit. And this is the telescope here. So you look in it right there. This can rotate about a vertical axis, and there's a scale right along there that tells you what direction you're pointing in. And it can also rotate about a horizontal axis here, and there's a scale along this arc that tells you what the inclination is. To use this, you simply set it up on a tripod here and look through it at eye level and look out towards the target. So there are two types of instruments. One, the simplest one, is a level, and this is designed to simply maintain the telescope in a horizontal plane. So here's an example of a level, and this thing can spin around, and you can use the scale right there on that ring to determine the orientation that you're pointing. You set it up initially using that bubble level, and that causes the device to spin around and cut a horizontal plane. So everything that once it's leveled, everything that you see through the telescope will be at the same elevation. Now a transit, it can function like a level, but it also allows the telescope to be inclined. So this old brass device is a transit, and this is a picture of a modern transit. This is a mechanical transit, so it has all mechanical parts. There are also electronic transits that have various different types of electronic instruments in them for performing the functions. So they're easier to use and in some cases more accurate than the mechanical devices. And then the other component of this system is a Stadia rod. That's a Stadia rod right there. So to use this, you have the transit, which is right there, set up on a tripod. You look through the telescope and you sight over to this Stadia rod right there. Okay, that's the general approach, and let's take a look at the Stadia rod itself, because this is one of the keys to the application. So these are two Stadia rods. They look quite different, but they have something important in common, and that is that they are basically just mechanical scales. So this is a scale this is 6, and it's going down to 5, which we can't see, it's off the page, but these are tenths of a foot right here, and each one of these is 100th of a foot. This is also a distance scale. This looks like it's probably in meters. And so what's going on here is this. If we look through the telescope, then we see something that looks like this. There's a crosshairs there in the telescope, and there are two tick marks right there and right there. And we can see this image of the crosshairs. There's a horizontal crosshair, and the vertical one is right there. And then these are the two horizontal tick marks. So what's happening is this. Let me draw the transit. And as you look through the transit, these two crosshairs optically are cutting an angle like that. And so this angle is it's a 1% angle. So the ratio of this distance to this distance is 1%. And what that means is if we know what this distance is, then we can determine this distance here, the distance away from the distance that the target is away from us. Okay, so the approach is to look at this Stadia rod through this telescope and line up the top, or line up the bottom crosshair, the bottom tick mark, and the top tick mark with these points on the Stadia rod. And essentially then you measure that distance by looking at where these marks hit on the Stadia rod. And then that distance is multiplied by 100 to get the distance that the Stadia rod is away from the transit. So pretty simple. The other thing that we'll want to do is also have this measurement here, right there on the Stadia rod. We'll use that to calculate the elevation. Okay, so the general strategy of using a transit and Stadia rod is similar to what we've used in the past, what we saw for doing the pace and compass. It's possible to do a traverse with the transit, but generally this is the strategy that's used, and that's because setting up the transit requires that it's leveled each time, and this takes a good bit of effort. And so you want to maximize the number of measurements that you can make that are useful to you with each setup of the transit. So what you might do is set it up right here at that location and then measure these points. And when you measure these points, you might go and sketch in a building that's there or some other feature of interest. You'll also be getting elevations. So you might write in the elevations, 9, 8, and with those elevations, you know, you could go and sketch in a contour. The 10 contour might look something like that. But eventually, you're going to shoot in all the points that are important to you that you can see from this location. And so you'll go and move this instrument by shooting over to another location here and determining the elevation of this location, and then moving the transit over to this new place right here. There's the transit. And then you start shooting in points from this location, and you get these points in. Now, before you start shooting those in, though, it's really important that the transit is located accurately. So when you set it up, the first point you should shoot in is this point right here, just to confirm that the location that this new location is determined correctly. If you don't do that and you're off with the transit location, then all these points will be off as well. Okay, so here are the types of calculations that you'll be making. I always like to draw a sketch in my field notebook about how I'm making the calculations and what I'm assuming each one of the variables means. If I'm using a level, then this is going to be the setup. I'll have an instrument height shown here, and then I'll shoot over, and I can only have a horizontal line, and that will hit on the Stadia rod at some height there. So I'll know this, and I'll measure this, and if what I want is the elevation change, then that will be determined by subtraction. And so I would make a little sketch that looked like this, and I would write that down. Now, if I'm using a transit and I'm turning vertical angles, then I can cover a wider vertical range. And so that allows me to have a line of sight that looks like this. And so I can get an elevation difference that's much greater than is possible using just a level. Okay, so if my transit is down on the ground, and I can shoot to a point that is also on the ground up here, then I can determine the elevation difference. If I measure this angle and I know this distance, then I can determine this elevation difference just as the tangent of the angle times d, and that's shown there. And this was the formula that we use for pace and compass, because when we're doing that, we're approximating what d is. But with the transit, it's going to be a little bit more complicated when we're turning these angles, because in fact we'll be measuring this distance, the line of sight, and so we're measuring L and not D. And in fact, we're not going to be sitting with our instrument on the ground, and over here where we're making the measurement, we won't be right on the ground either. We'll have this Stadia rod. And so the configuration looks really more like what's shown here. We've got an instrument height, we've got this angle that we're turning, we've got a height on the Stadia that we're measuring by looking through the telescope. And we put all that together, and what we're really after is the difference in elevation from the elevation of the ground surface here at the instrument and the elevation of the ground surface here at the Stadia rod. So what we can do is, from geometry, we can get that difference there. That would be L, that distance, times the sine of alpha. And then, so let's see, that gives us this. Let me just erase all this stuff here so I can draw it a little bit clearer. Okay, so this is what we want. And right here, that measurement, that's L sine of alpha. And so pretty clearly, I think, that in order to get this distance, what we need to do is, the way to do it is to take that distance and add to it that distance. Okay, well, this distance here is what I'm calling H1, the height of the instrument. And this guy here would be L sine of alpha minus H2. So that's the elevation difference. Okay, so it's some fairly straightforward geometry, but it's important that you get it right, and the best way to do that is to draw out a sketch and label the sketch, and then just make sure that you're comfortable that the calculations that you're doing are correct. And I would write down these calculations. Okay, so surveying will involve making measurements at a bunch of different points, and the best way to do this accurately is to get a routine. So you make the measurements using the same techniques, and you record them in the same way. And a good way to do this is to set up your notebook with columns and label the columns and write down the same data in each column. So this is an example, and in this first column we give the point a number, and I would plot the map as I go, and so this might be P1 and P2, and I would write that identification number next to the point on the map. And then the azimuth, this is from the transit. These are from sighting to the Stadia rod. The middle intersection, these are the upper and lower tick marks. Then the distance, this will be the upper minus the lower times 100. Write that in there. And then the inclination, and this will be measured from the transit. And then E1, and E1 would be, there's E1. So we said that was L sine of alpha. So I'd write that in there. And then the elevation, that's what we actually want to calculate. And so I would write down a formula for that. And we said that that was E1, well, let's call it E, equals E1 plus H1 minus M. And M is the measurement on the Stadia rod. And then this is going to be the elevation relative to the elevation of the transit. Well, relative to the place where the transit is. We're going to want to have all of the elevations measured relative to the same datum, though. So on the data sheet, I'm writing down here the elevation of the transit right there. And so that's going to be added on to every measurement. So basically, here's what we've got. Let me do a little sketch. Let's see up here. So here's the instrument. And we'll shoot up in the air like that. Here's the Stadia rod. That would be M. This would be L and U. The azimuth isn't going to be shown here. That's alpha right there. The distance, that's L right there. E1 E1 is that. H1 is that. And if this is the datum, that's E0. So that's the elevation of this point in the field. Okay, so if I have all of that and I take this formula and then add to it E0, then that will give me there the elevation of that point relative to a common datum. So I would have a new E0 each time I move the transit, and I would have a new transit location, and I would describe that in text, and I would do that each time I move the transit. Also, each time you set up this transit, the legs of the tripod will be somewhat different, so the height will be different. So each time you move the transit, this information will change, and then you'll have this set of data that you'll measure at that location. Okay, so that'll be the strategy. The overall approach is given here, and it's really very similar to the approach that we looked at when doing pace and compass. The only difference we saw on the previous slide is that you'll probably want to shoot many points from a single location rather than just shooting one or a few with the pace and compass. Mechanical transits typically use a Vernier scale to improve the resolution of their angular measurements. This is a Vernier scale shown here, and this is set up to improve the resolution of the inclination measurement on this transit. This is the telescope up here, and there's an angular scale that looks like this that has some ticks like this, and it's attached to this telescope. And as the telescope rotates, it moves with the telescope. This scale down here is fixed to the base, and so the upper scale moves relative to the lower scale. So if we zoom in on this, we see the two scales, and the upper scale here, that's in units of degrees. The lower scale, it goes from 0 to 60, and these are in units of minutes. A minute, 60 minutes divides up a degree, and so the lower scale, the Vernier scale, is going to be what we use to interpolate the value to the nearest minute, so we can get better resolution than simply getting to the nearest degree. Okay, so the way it'll work is we'll be looking to line up the ticks on the upper scale with the ticks on the lower scale. So let's take a look here at this example. So the upper scale is rotated and the telescope is inclined like this. You can see 0 right there. So to make a measurement, we go in this direction till we get to the 0 point on the base. So there's 5 degrees right there, 6, 7. So the 0 scale is between 7 and 8 degrees. And in order to interpolate between 7 and 8 degrees and see where it's falling, we continue on and we look at the offset of the ticks. So there, the ticks on the top and the bottom scales are offset a bit. The scale on the top is offset a bit to the right. But as we move in this direction, the offset lessens. And then right in here at about 30 degrees, the two ticks line up. And then as we continue on, you can see that we get an offset where the tick on the upper side is offset to the left. So it's just the opposite from the offset here. So what we do is we find where the ticks are lined up, and we use that reading to interpolate between these two readings here. Okay, so in this case, the angular measurement would be 7 degrees and 30 minutes. 30 minutes is halfway between 7 and 8 degrees. And so that allows us to determine that interpolation with a lot higher resolution than we could do just by trying to read this scale right here by itself. Okay, so let's take another look at this example. So here we've tipped the scale, or we've tipped the telescope like this, and right there is 0, and it's lining up with, well, this 0 here is lining up with that tick right there. So you can see it's 1 degree and getting close to 2 degrees. In fact, we might call it just 2 degrees. But let's see, maybe it's not quite 2 degrees. So we take a look at the ticks, and right here, those ticks they're not lined up, they're offset. And as we head on in this direction, the offset gets even more. And now it gets to be less. And it looks to me like right here, those ticks are lined up. And it looks to me like the alignment there is a little bit better than at 60. So what I can do then is to say that the angular difference is 1 degree and, come up here, 55 minutes. And because it's going in this direction, I use the negative sign to distinguish it from the previous direction that we saw on the last slide. Okay, so here's some more examples. This will be similar to what we saw in the previous slide, where we've got 1 degree and then the tick is between 1 and 2 degrees. And to find out just where it is, we go basically the way it's going to work is we go from 0 and we make the reading, and then we keep on going in that direction. And we look for where these ticks lined up. And it looks like it's right there. Okay, and that reading is going to be, there's 15, 20, 25 degrees. Okay, and that's 25 minutes. Okay, so the reading is 1 degree, and then we interpolate between 1 and 2 degrees using the vernier, and then we get 25 minutes. So here's the next reading. We start at 0 and go in this direction. And there's 1, 2, 3, so it's between 3 and 4 degrees. And to find out where, we keep going. We look for where they line up. And That looks like yeah, it looks like it's right here. And if we come across, that is 10 minutes. Each one of these tick marks is a unit of 5 minutes. So there are 2 tick marks from 0, so that's 10 minutes. Okay, so let's try it again. So we're starting here, and so this is tipped like this, and we go and make a reading. There's 1 degree, there's 2 degrees, and we go continue on this direction. You find that they're lined up right there. So this is 1 degree, 55 minutes. The same example that we saw earlier. Try it again. So this is, here's 0. This is tipped like that, so it's going to be a negative angle. And we go 1, 2. It's between 2 and 3. And we continue on this way. And that's where the 2 ticks line up. And so there's the reading in minutes. So it's -2 degrees and 30 minutes. Okay, so this is the example that we saw at the beginning. And initially when we looked at this, we thought that it was at 0. And so it looks like that and that lined up pretty good. But I think if you look at this carefully, you might see just a little bit of offset there, and just a little bit of offset there of the opposite direction. And this one in between looks like it's lined up a little bit better than the 2 on either side. So this isn't exactly 0. This looks like it's at about 5 minutes.